Hello, everyone, and thank you for attending today's webinar, Behind NEC 2014 and 2017, What Solar Installers Need to Know. I'm Kelsey Misbrenner, editor with Solar Power World. Before we begin, we wanted to let you know about our application widgets at the bottom of your screen. You can move and resize them how you like. Slides are available to view at any time via the resource widget. Submit any questions related to today's webinar via the Q&A widget. Our presenters will send answers afterward to the email you used to sign up for today's webinar. We encourage you to tweet with us. Simply sign in through the Twitter box. Today's hashtag is automatically added to your tweets. And finally, if you're watching this on demand, you can still use all the features I went over. Let's get started with today's webinar, Behind NEC 2014 and 2017, What Solar Installers Need to Know. Today's speakers are Eric Lorenz and Michael Neiman. Eric is a technical sales manager with 9 years of experience in construction and electrical PV construction. He is both a private and municipal grid interconnection specialist. Michael is a senior applications engineer with over 8 years of experience in the solar power and electrical construction industries. He graduated from the University of San Diego with an electrical engineering degree. And now I'll turn it over to Eric.
Inverters are at the heart of every PV system. As such, there are many features to look for when specifying these units to help you achieve safe, code-compliant PV systems. CivicSolar looks for these distinguishing features in string inverter options: arc fault protection, interruption, ground fault detection, multiple MPPT or module level power electronics capability, integrated disconnects, rapid shutdown capability, and easy to deploy monitoring solutions. The Scala Selectria equipment are excellent examples of products that include these features. Arc fault detection was introduced in the 2011 code cycle. At that time, products were not readily available, resulting in little to no enforcement of the requirement. Over time, products became available such as string inverters with onboard arc fault detection. Ground fault detection was introduced in the 1987 code cycle and has since seen many modifications. Originally placed in 690.5 and 690.35c for ungrounded systems, it was moved to 690.41 in the 2017 code cycle. Ground fault detection is an important feature to assist in the prevention of fires. For system designers, installers, and owners, inverters incorporating these two features simplify system design, operation, and maintenance. Inverters that have multiple MPPT trackers allow for more design flexibility practices such as different string lengths, varying array orientations, and reduced BOS needs. Further, system owners can expect greater kilowatt-hour yields and reduced BOS costs, resulting in more favorable return on investment. Inverters that have module-level power electronics capability experience all of the benefits of multiple MPPT tracking and more. When MLPE is introduced, greater annual kilowatt-hour yields can be expected, better insight into the array operation can be achieved, and most notably, the ability to meet NEC 2017 Rapid Shutdown requirements. More to come later on the webinar regarding these requirements. The NEC requires that the PV system have a means to be disconnected from all other electrical systems. That's 690.13. Additionally, PV system equipment must have a means to be disconnected from all electrical sources in 690.15. Inverters that have integrated disconnects make it easy to meet these requirements. As for rapid shutdown, it is important that the inverter manufacturer provide or specify a solution to meet NEC 690.12. An important feature that is many times overlooked in inverters is the integrated disconnects. Units that have integrated AC and DC disconnects make system design and installation easier, reduce BOS costs, and simplify maintenance and troubleshooting efforts. Now to the code. Here are two snapshots of where the country is in terms of current code adoption and code adoption in progress. The figure on the left shows the current adopted code cycle per state throughout the country. As you can see, the adopted code cycles vary greatly. NEC 2008 through NEC 2017 is being enforced with the majority of the country, 72%, enforcing 2014. The figure on the right shows the adoption process per state. 50% of states are in the process of adopting NEC 2017, while 34% of the states are going to stay with their current code cycle. The code, as you all know, is ever evolving, with changes made every 3 years. Here are some important changes that have occurred throughout the last 3 cycles. In the 2011 code cycle, arc fault 690.11 was introduced. Additionally, fuse servicing was introduced in 690.16b, ensuring a safer environment for those servicing and maintaining PV arrays. In the 2014 code cycle, the arc fault requirement was revised to be included on all PV systems regardless of their location. Ground fault protection was revised to have a more thorough requirement of detecting ground faults in the grounded conductor. And as all of us all know, the requirement for rapid shutdown was first introduced. In the 2017 NEC, a major revision occurred. Of the many changes, notable ones are the redefinition of the PV system boundary, a new definition of functionally grounded, a major overhauling of rapid shutdown, and arc fault now has an exception to systems not on or in buildings. The introduction of the definition of functional grounding, a PV system that has an electrical reference to ground that is not solidly grounded, has many design implications that the PV industry will benefit from. The most important is that we will now apply a single set of design parameters to both functionally grounded and ungrounded PV systems. Major implications include the reduction of overcurrent protection in circuits. Disconnecting means are required in both legs of a PV circuit, and the use of used-to or PV wire and single conductor cables are both now allowed to be used within PV arrays. The 2017 code cycle introduced a more explicit PV system boundary to which 690 would encompass. The PV system boundary is now considered the point where the PV system equipment couples with other sources on the same electrical system. As such, the PV system boundary varies depending on system type. Further, energy storage systems are no longer covered in NEC 690 and have their own place in Article 706 of Chapter 7. 2 examples of PV system boundaries where the PV system disconnect is located and the PV system is coupled are shown above. The first is a DC coupled system and the second an AC coupled system. In both cases, there is energy storage present to which the NEC 706 would encompass. In the DC coupled system, the PV system boundary would be considered the PV system disconnect. In the AC coupled system, the PV boundary would be considered the AC disconnect on the output of the interactive inverter, which would be the same as in a purely interactive system. The intention of introducing rapid shutdown in the 2014 code cycle was to provide a safer environment for emergency response personnel. Rapid shutdown only applies to PV systems on or in buildings. The code calls for controlled conductors to meet certain requirements based on their location in relation to the physical PV array or arrays. Controlled conductors are those that are 10 feet away from the PV array on the outside of a building or 5 feet within a building. The controlled conductors shall be limited to 30 volts and 240 volt amperes within 10 seconds of rapid shutdown initiation. However, a tentative interim amendment, TIA, has been issued regarding this requirement of rapid shutdown, which states that the initiation must happen within 30 seconds, the same as in 2017. The 2014 rapid shutdown labeling requirement is quite simple. A label must be installed stating photovoltaic system equipped with rapid shutdown. The 2017 version of rapid shutdown is far more detailed and has more stringent requirements when compared to the 2014 version. The term controlled conductors is the same, except now there are 2 distinct areas with different controlled values. 690.12b1 refers to conductors outside the array boundary, and 690.12b2 refers to controlled conductors within the array boundary. Controlled conductors outside the array boundary must be limited to 30 volts or less in 30 seconds. Controlled conductors within the array boundary must comply with one of 3 options. First option is PV array must be listed or field labeled as a rapid shutdown array. The second option, controlled conductors within the array boundary must be limited to 80 volts or less within 30 seconds. The third option, which allows for building integrated PV arrays, states that no exposed wiring methods, no exposed conductive parts could be installed, and they must all be installed outside of 8 feet from exposed grounded conductive parts. If it meets this third option, then you do not have to apply with the second option. The requirements of 690.12b2 will not become effective until January 1st, 2019. This allows for the industry to catch up with the code by manufacturing listed equipment, as well as to develop product safety standards for rapid shutdown arrays. The 2017 version of Rapid Shutdown also introduces the requirement for a rapid shutdown initiation device. This device must consist of one of the following: a service disconnecting means, a PV system disconnecting means, or a readily accessible switch. The 2014 labeling requirement for rapid shutdowns is quite simple. A label stating PV system equipped with rapid shutdown is required. The 2017 identification of power sources labeling requires much more detail to be provided. First, rapid shutdown type must be presented. Types include systems that shut down the array and conductors leaving the array, and the second would be systems that only shut down conductors leaving the array. If a building has more than one rapid shutdown type installed on it, a detailed plan view showing which arrays are controlled by which type of rapid shutdown must be installed. Finally, the rapid shutdown initiation device must be labeled with a placard that states rapid shutdown switch for solar PV system. At this time, I'd like to hand the floor over to Michael Neiman, Senior Applications Engineer of Yaskawa Selectria Solar.
That solar installers face today. I'd like to spend a few minutes discussing some of the products Yaskawa Selectria Solar has available to the market and highlight what we're doing as an equipment manufacturer to help installers such as yourselves comply with the various code requirements. As a leading three-phase commercial inverter supplier, the products and solutions I'm going to highlight today are really focused on the C&I space. But keep in mind that much of the application is applicable to the other market segments as well. Selectria provides a wide range of three-phase transformerless string inverters. A lot of flexibility, perfect for the commercial, industrial, rooftop projects. These units come in a variety of power classes: 14, 20, 23, 28, and 36 kilowatt machines. The 14 and 20 kilowatt inverters are designed for 600 volt DC arrays, while the 23, 28, and 36 are designed to be used with 1000 volt DC systems. The 14 kilowatt machine is a 208 AC output, while the 20 through 36 are designed for 80 volt connections. These transformerless string inverters have a best-in-class efficiency over 98%. As you see in the picture, they're lightweight, compact design, very installer-friendly, important when working on rooftops or crowded, preoccupied electrical closets. These units have integrated and lockable DC and AC disconnect switches. This is great as it alleviates the requirement for a separate external or adjacently mounted disconnect switch. The units have an integrated string combiner box with fused inputs. The 14 through 28 TL have 8 fused inputs, or 4 per MPPT channel, while the 36 actually accepts up to 10 fused inputs, or 5 per channel. All these machines have dual MPPT inputs, which give you the flexibility to design accordingly. Various string lengths, different module manufacturers, different array orientations, and different mismatch mechanisms can be accounted for. The integrated string fusing and the DC-AC disconnects meet the NEC requirements that Eric previously mentioned. Moving to NEC 2017, we'll see that some of the code requirements are actually going to begin deriving change in the way equipment manufacturers such as Selectria provide solutions to the market. For example, today we break both the DC poles and we fuse both positive and minus poles on the string inverters. As more states adopt 2017, we'll be able to remove parts and cost optimize as necessary to remain code compliant and competitive in the industry. Other features I'd like to highlight on these products are we can accept aluminum conductors for the AC connections. This allows long industrial feeders the ability to use low-cost materials and still meeting volt drop requirements with large conductor sizes. Finally, Selectria can offer a variety of options with these products, including shade covers if installed on hot, harsh environment rooftops, web-based monitoring services, array brackets, and DC combiner box bypass kits, which will be utilized later when I talk about our RSDCOM, or our Rapid Shutdown combiner products. The PVI 50 and 60 TL are Selectria's newest offering of three-phase transformerless string inverters. These units are 1,000-volt DC inverters, 50 or 60 kilowatt power classes with a 480-volt AC output. These inverters have 3 MPPT input channels, each with 5 string inputs apiece. The integrated combiner box allows for up to 15 string inputs from the array, eliminating the need for an external combiner box. This is significant savings on your installed BOS costs. The 3 MPPT trackers also allow you to harvest the maximum energy yield from the array and gives you flexibility in the array design and installation, allowing for varying string lengths, different module types, or even different array orientations. Similar to the other products in this family I just talked about, these units have integrated AC and DC disconnects, allowing you to comply with the NEC 2014 and 2017. These units come standard with integrated arc fault circuit and interruption capabilities and industry-leading communication requirements, including SunSpec compliance, remote firmware upgradability, and the ability for Selectria Service Department to perform remote diagnostics on the units. Now I'd like to introduce Selectria's Rapid Shutdown combiner box. This product is designed to be utilized with Selectria's three-phase transformerless inverter family, the PVI 14 through 60 kilowatt units that I just discussed. This is an external combiner box solution designed to meet the National Electric Code Article 690.12 requirements for array-level rapid shutdown. This box comes in a variety of flavors. We can support single or dual MPPT zones, depending on the inverter technology, as well as the array layout for your PV system. The boxes utilize a control power signaling to allow you to initiate the rapid shutdown at the same location as your main electrical service and inverter connection points. This product is also compatible with third-party inverters, so long as the zone input capacitance of that inverter is below 65 microfarads. If you have any questions about the technical requirements of this product or its application with other non-Selectria inverters, I encourage you to contact the Selectria staff. This product can be provided with a number of options as well. Surge arresters to eliminate strike potential on the DC side of your array, as well as H4 or MC4 pre-wired whips, if this would be a benefit to your string wiring on the array. Additional features of the RSDCOM worth highlighting. These products include an external contactor-based disconnect switch. This switch allows you to remotely disconnect the combiner from feeding the PV energy back to the inverter. These combiner boxes are available with different fuse quantities per zone. We can offer these solutions with either 4 or 5 fuses, depending on the array configuration and how many strings of PV source circuits you have going to the inverter MPPT zone. The RSDCOM combiner boxes include an integrated inverter capacitance Boolean diode circuit. As Eric mentioned, on the National Electric Code requirements of rapid shutdown, there's a time duration within which we must reduce the voltage level of the home run circuits back to the inverter. Inverters are switching electronic devices and include capacitors which hold a charge and may not naturally discharge within the required time frame. Selectria includes this bleed down circuit integrated to the RSDCOM in order to drain any inverter capacitance that may hold that voltage level above the minimum required threshold. These boxes use a remote control power source to signal the rapid shutdown. This source can be simply supplied as the same source that it supplies the string inverters, allowing a single point of disconnect. Here is a simplified schematic view of how the RSDCOM can be used in conjunction with the Selectria TL string inverter to meet the array level rapid shutdown compliance of either NEC 2014 or 2017. On the left, you see a picture of a solar array with your PV source circuits inputted directly to the rapid shutdown combiner. The output of this combiner are PV output circuits, which feed directly into the PVI 14 through 60 TL string inverter. You'll see depicted at the bottom, the RSDCOM location should be within the maximum distance required by the National Electric Code, 10 feet for NEC 2014 or 1 foot for NEC 2017. Additionally, you see the need of the external control power source, 208 to 277 volts AC, which is easy to be provided from the same source of electricity providing power to the inverters. For a quick view under the hood of the RSDCOM and some of the internal components that we provide with this product. The first thing you'll see are the touch-safe fuse holders. Again, we can provide 4 or 5 fuses per MPPT channel with this product. These touch-safe fuse holders support 15 through 30 amp source circuit fusing, allowing you to use different module sizes or employ new methods of source circuit wiring, including Y connectors or parallel strings, if desired for your overall system installation. Additionally, in this overview, you can see the surge protection device provided, available as an option with this product. On the right side of the enclosure, you'll see the 2 contactors. These contactors provide the isolation from the source circuits to the output circuit wiring. These contactors open up when a rapid shutdown is initiated, and thus isolating the home run segment of conductor between the combiner and the inverter. Additional electronics in this box include the bleed and control board, as well as the AC power supply. The AC power supply is where you'd interface the control power, control signal circuit to allow you to initiate the rapid shutdown. On the right is the disconnect switch, allowing you to locally disconnect the combiner box. Now that I've briefly overviewed the product solutions Yaskawa Selectria Solar has to comply with rapid shutdown, I'd like to spend a few minutes showing some design practices that you may be able to employ in order to achieve code compliance with rapid shutdown. Here is an example of a very cost-effective way to meet the array level rapid shutdown requirements of NEC 2014 and 2017. For rooftop installations where the roof is flat and accessible, it may be possible to install the inverters within the array boundary. In this case, the AC conductors leaving the inverter to your building electrical closet are the only conductors subject to the rapid shutdown requirements. When the AC disconnect switch is closed, these conductors are energized. When rapid shutdown is initiated, the switch is opened, the AC conductors go dead, and the inverters stop energizing due to the requirements of anti-islanding. So long as you can install the inverter within the array boundary, this may be the most cost-effective solution for you to meet the array level rapid shutdown and not require any additional equipment beyond the use of transformerless string inverters. When it's not possible or not feasible to install the inverters within the array boundary, you can utilize the Selectria RSDCOM combiner box product. In this case, you would install the combiner box within the array boundary being 10 feet for NEC 2014 or 1 foot for NEC 2017. This combiner box now has the responsibility of isolating the PV output circuits, leaving the array and going to the inverter. In this example, the combiner boxes have a control power source present. When rapid shutdown is initiated, that control power source is deactivated. The contactors in the RSDCOMs open up, and the array is now isolated from the inverter. The DC output circuits transmitted from the array to the inverters are now de-energized. Additionally, the RSDCOM will bleed any inverter capacitance that may be on those output circuits, being held by the inverter's capacitors if they're not able to naturally discharge within the allotted time frame defined by the National Electric Code. This diagram highlights the use of Selectria TL string inverters coupled with Selectria's rapid shutdown combiners in a code-compliant installation. In this example, we have a PV system that is segmented into 3 array sections. This is often the case with larger commercial and industrial rooftop PV projects. A rapid shutdown combiner would be installed within the NEC-defined boundary of each array section. For discussion purposes, let's assume the top array section is comprised of 8 PV strings. These 8 strings would connect to a single 2-zone rapid shutdown combiner. The output from this combiner would be paired to a string inverter. For the lower 2 array sections, let's assume they are half the size of the first, or 4 PV strings apiece. The strings from each of these array sections would connect to their own 1-zone combiner. Then, the outputs from both combiners would be paired to another string inverter. With our array defined, let's discuss how this equipment works together to achieve code compliance. As I explained previously, the rapid shutdown combiners require an external control power circuit to function. Most often, the PV panel board is the most logical source for this circuit. Whether it's a 208-120 or a 480-277 service, an extra circuit from this panel can be allocated to supply control power to the combiners. With the system disconnect closed, as shown on this slide, the inverters, the rapid shutdown combiners, and the PV output conductors are all energized and operational as conditions permit. Now, in the event first responders need to initiate a rapid shutdown of the PV array, the system disconnect is opened. The inverters will lose their AC source and disconnect immediately. In a similar fashion, the rapid shutdown combiners will lose their control power. When this happens, their internal contactors will open, which isolates the PV output conductors from the PV source circuits. Lastly, the bleed circuits internal to the rapid shutdown combiners will help drain any inverter bus capacitance that may be still energizing the PV output conductors. Assuming the installer did their part to label and identify the system appropriately, you'll have a code-compliant system. Early adopting state, or you have a client that already wants to comply with module-level shutdown. What can you do? What solutions do you have? Well, again, to reiterate, the requirement of 690.12b2 is not officially effective until January 1st, 2019. That means today, even in 2017 jurisdictions, array-level rapid shutdown is really where the requirements end. Currently, CivicSolar has solutions for code compliance for all market segments. Array-level rapid shutdown for our residential single-phase product line. CivicSolar has solutions for all market segments. For residential products, our single-phase inverters, we have a residential rapid shutdown combiner. For our TL inverters, commercial industrial projects, the solutions I've talked about today. As I remind you, you can install the inverter within the array boundary or utilize an external contactor rapid shutdown combiner. But what about module level shutdown? What about disconnecting, de-energizing within that array boundary? I know it's not effective until January 1, 2019, but certainly installers and clients, want that functionality today. So Selectria PVI 23, 28, and 36 TL inverters are fully compatible with the Tigo TS4 platform. Tigo is a module-level electronics manufacturer, and their TS4 platform provides that module-level shutdown, that module-level safety, which is compatible with our 3-phase transformerless string inverters. Additional to this, we're evaluating several other options in order to achieve compliance with that 690.12b2 article of the 2017 code cycle. This includes qualifying additional third-party products that we can package and recommend our inverters with, similar to the Tigo TS4 platform. We're also working behind the scenes with the leading module manufacturers on simplified integrated electronics. So, switches, devices internal to the modules at the module junction box. make a lot of sense for module level shutdown. And we're working to follow the industry trends and harmonize with the other work going on within the industry. SunSpec Alliance is one example of a great outfit that's doing a lot of work to harmonize the inverter on a communications protocol. It's easy to imagine one day that inverters can communicate uniformly with module level electronics, really to be kind of the hub of PV systems when we talk about module level shutdown and other safety code requirements. It makes a lot of sense for an inverter to talk agnostically to other third-party equipment solutions and ultimately make your life as an installer more plug and play from an equipment selection standpoint. Selectria is pleased to announce our compatibility with Tigo Energy's TS4 platform. The TS4 platform, module-level electronics, includes a family of devices that are either pre-integrated with the module or can be supplied as a retrofit in a separate junction box that's installed separately to the module. This family of products has a variety of feature sets which can be deployed selectively depending on the requirements of your specific array. Most notably, the TS4S model is a safety switch which allows you to meet module-level shutdown. The TS4 platform performs module-level disconnecting with the TS4S safety, TS4O optimization, and TS4L long string variants. Electronics are built into these module junction boxes, does not require extra parts. The retrofit family can be easily added to existing installations in order to bring that system up to compliance with current code. In summary, I'd like to reiterate the various ways that you can comply with some design practices for rapid shutdown compliance. If your installation is in 2014 jurisdiction, the simplest manner may be to install the inverter within the array boundary. This again allows you to meet the array level rapid shutdown and may not require any additional external combiner boxes or rapid shutdown equipment. If the inverter cannot be installed within the array boundary, we have the RSDCOM product, which can be coupled with the Transformerless string inverter in order to meet the array level rapid shutdown. Finally, you may be able to use approved MLPE, such as the Tigo solution, to perform module level shutdown and in effect also meet the array level rapid shutdown. If you're in a 2017 jurisdiction prior to January 1st of 2019, again, you can install the inverter within the array boundary. This will allow you to meet the array level rapid shutdown. Or use an RSDCOM combiner box coupled with the string inverter and again improved MLPE. A year and a half from now, January 1st, 2019, to comply with the 2017 code, an approved MLPE device will be required, unless the installation is a building integrated PV system, as Eric introduced previously.
Now we're going to open up the floor for some questions. Remember, you can continue to submit questions at any time in the Q&A widget. First question, I don't really understand what function grounding means. Is this going to completely forego traditional grounding in the PV circuits?
I can take this one. Functional grounding refers to a connection to ground that is not solidly grounded. Traditionally in PV systems, the connection to ground has been through a fuse or overcurrent device to meet the requirements of 690.5 ground fault protection. In doing so, the systems were not solidly grounded. They were functionally grounded.
All right, the next question.
Can I jump in real quick from the equipment manufacturer standpoint? So what we're doing, speaking for Selectria, is our Transformerless three-phase string inverters. We don't solidly ground the DC side of the array. We incorporate overcurrent protection currently on both poles of the DC array, which is in compliance with the 2014 code. And we additionally break both legs of the array through the DC disconnect switch. What you'll see from equipment manufacturers as the 2017 code is adopted more widespread, that we will be able to take into account cost-reducing strategies to reduce component count and ultimately increase product reliability based on the new rules defined by 2017 with the new introduction of the definition of functionally grounded.
All right, thank you. The next question is, why did they choose to make the amount of time longer for the voltage to drop?
What I think you're referring to is the rapid shutdown requirement, changing from 10 seconds to 30 seconds. The 2014 rapid shutdown requirement, as it was being compiled, the need for a grid ride-through was not considered, or it was overlooked. Many utilities, though, require at least a 20-second ride-through to allow for any type of utility disturbances. Therefore, if rapid shutdown was initiated within the 10 seconds, as in 2014 requires, these PV systems or arrays would be shut down and would not be turned back on in a timely manner. So the code cycle in 2017 revised this to allow for those utility disturbances to occur.
All right, the next question is, doesn't 690.12b3 say that as long as the arrays are installed well, they don't have to abide by the code and would make all module level rapid shutdown not important?
This particular portion of the code allows for building integrated arrays to be installed. And these arrays will not have to comply with the requirement of 690.12b2. This allows for them to be installed when they don't have when they have raceways that are concealed. The array doesn't have any type of conductive component, and they're installed within or outside of 8 feet from any type of grounded, electrically grounded system.
The next question is, what does the timeline look like for implementation of NEC 2017 for states that are on board?
Great question. As Eric reviewed previously in the presentation, we showed some maps of the current state of adoption on a state basis. I encourage everyone joining in today to view the resources available on NEMA.org, the website. They have these maps and additional details showing the current status of, on a state basis, of which code cycle has been adopted. And additionally, they have another PDF document outlining kind of the roadmap to future adoption by other states or other jurisdictions and what the current plan is kind of forward-looking. Selectria, we're in a unique position that we're headquartered in Lawrence, Massachusetts. Massachusetts is also the home to the National Fire Protection Agency, the authors of the NEC. So Massachusetts is always an early adopting state, and we've had customers in our backyard having to comply with the 2017 and new and improved rapid shutdown requirements from the onset. So we've had some time catching up to the code requirements and been able to offer rapid shutdown solutions since the forefront of the requirement.
The next question is, what do you think is the next logical step for rapid shutdown with NEC 2020?
Another great question. What you're going to see from equipment manufacturers is harmonization to allow inverter technologies to communicate directly with module integrated electronics and switches more specifically. There's a lot of work being done in the industry. SunSpec Alliance is one organization working on a communication standard to define what that communication may look like between inverters and module integrated electronics to allow for a uniform command structure to initiate rapid shutdown of PV arrays.
Thank you. That is all the questions we have time for today. If you have additional questions or we didn't get to yours, feel free to contact our presenters on your own. Again, this webinar will be shared with all registrants, so you may view it again at your convenience. I'd like to thank Eric and Michael again for being here, and CivicSolar for sponsoring today's webinar. And thank you to everyone in our audience for participating. I hope you enjoyed our presentation, and we invite you to join us for more Solar Power World webinars. Thanks, everyone.